Welcome to Thought Frontier.
Welcome back to the Deep Dive. Today we're diving into this super exciting, always evolving world of superconductivity research.
Superconductivity.
You know, our listeners are always on the edge of their seats waiting for news on room temperature superconductors.
Always. It's the holy grail, isn't it?
Absolutely. So we've got three really interesting sources to dig into today.
Okay, lame on me.
First, a news piece from Live Science. They highlighted a surprising discovery in a very unexpected material.
Unexpected, huh? I'm intrigued.
You and me both. Then we've got an article from Rice University about a breakthrough in understanding a special type of magnet, a kagome magnet.
Kagome magnets. Fascinating stuff. Lots of potential there.
That's what I thought. And they think it might offer clues to better superconductors.
Okay, I'm hooked already. What's the third one?
Last but not least, a report from the Simons Foundation. It's about a major achievement in computational modeling.
Oh, so they've managed to simulate.
Yeah, they've simulated the behavior of high-temperature superconductors. Pretty amazing, right?
That's a big deal. Could really move the field forward.
That's what I'm thinking. So the question we're exploring today, are we closer to room temperature superconductors than we think?
All right, let's dive in. I'm ready.
Me too. But before we get ahead of ourselves,
Right.
maybe we should take a step back for a second.
Back to basics.
Yeah, just to level set. What makes high-temperature superconductivity so difficult to achieve in the first place?
It all boils down to this.
Okay.
For the longest time, we only saw superconductivity at extremely low temperatures.
Like near absolute zero, right?
Exactly. We're talking insanely cold. And that's because superconductivity is all about electricity flowing with zero resistance.
Which is amazing.
Absolutely amazing. And the key to that is electrons pairing up at these super low temperatures to form what we call Cooper pair.
Cooper pairs, okay. And what's so special about these pairs?
Well, think of it this way. Normally, electrons would repel each other, right?
Wait, like charges repel.
But in these Cooper pairs, they actually become bound together. And not only that, they move perfectly in sync.
Wow, so they're not just paired, they're like a perfectly choreographed dance team.
Exactly. And because there's no resistance, electricity can flow freely without losing any energy.
That's incredible. But then along came cuprates, right? Those copper-based materials that shook things up.
Oh, yeah. Cuprates were a game changer.
They could superconduct at much higher temperatures. Still cold, but a huge step forward compared to what we'd seen before.
Huge. And that discovery really kicked off the race to find materials that could superconduct at even higher temperatures, eventually room temperature.
Which brings us to that Live Science article I mentioned.
Okay, the one with the unexpected material.
Exactly. It's about a material called neodymium cerium copper oxide.
Okay. And what's so special about this one?
Well, get this. It's an electrical insulator.
An insulator. That doesn't sound right.
I know, right? You wouldn't typically associate an insulator with superconductivity at all.
You'd think it would be the last place to look.
Right. But here's where it gets interesting.
Okay, I'm listening.
Scientists observed electron pairing happening at temperatures much higher than you'd expect for this material.
Interesting. So how high are we talking?
Well, still nowhere near room temperature. We're talking minus 190 degrees Fahrenheit.
Still pretty chilly.
Yeah. But get this. It's significantly warmer than the temperature at which it actually starts superconducting.
Hold on. So it shows signs of electron pairing at one temperature,
Uh-huh.
but doesn't actually reach a zero resistance state until it gets much colder?
That's exactly it. Like the electrons are sort of flirting with superconductivity. They're showing potential.
But not quite ready to commit until things get really, really cold? I see.
So what's holding them back?
Well, that's the big question, isn't it?
The million-dollar question.
They're forming those Cooper pairs, but they're not quite synchronized enough to hit that zero resistance state until the temperature drops significantly.
I wonder why.
It's a puzzle. But here's the thing. This finding suggests that the conditions for superconductivity might already exist in materials that we'd normally overlook, like insulators.
That opens up a whole new world of possibilities, doesn't it?
Absolutely. It's a whole new way of thinking about where to look for these materials, and it's only the first article.
I know, right? Wait till you hear about these kagome magnets. Kagome magnets, they sound so cool.
Oh, they are. They have this unique structure that's got physicists all excited.
Yeah, the article mentioned something about a Japanese basket weaving pattern.
That's right. Imagine a lattice of atoms arranged in a repeating pattern of triangles and hexagons.
Okay, I can picture that. But why all the fuss about this particular pattern?
Now, it turns out that this kagome arrangement can lead to some pretty unusual electron behavior
Unusual how?
in ways that we think might be connected to superconductivity. See, the electrons in these kagome lattices can get sort of stuck. Yeah, localized. They can't move freely throughout the material like they normally would.
Interesting. And the Rice University article, this was about a breakthrough in understanding how these magnets work.
Exactly. They were looking at iron tin thin films, which are a type of kagome magnet, and what they found really challenged our previous assumptions.
Okay, so what did they find?
We used to think that the magnetism in these materials was driven by the mobile electrons, the ones that are free to zip around.
Makes sense.
But this research shows that it's actually the localized electrons, the ones that are kind of stuck, that are responsible for the magnetic properties.
Wow, so we were looking at the wrong electrons all along.
Pretty much. And this could have huge implications for understanding superconductivity, too.
Because?
Because if we can understand how these localized electrons behave in kagome magnets, maybe we can figure out how to manipulate them in other materials, even superconductors.
So it's about controlling those stuck electrons.
It's like finding a new knob to tune how electricity flows.
Okay, that makes sense. So we've got these strange insulators showing hints of superconductivity and a new understanding of how kagome magnets work.
Uh-huh.
Now let's talk about that Simons Foundation report.
The one with the computational modeling.
That's the one. They were looking at high-temperature superconductors, right?
Yep. Specifically, they were trying to simulate the behavior of cuprates.
Those copper-based materials?
The very same.
And they were using this thing called the Hubbard model, right?
You got it. It's essentially a simplified way to represent how electrons move and interact in these materials.
Simplified, because the real thing is just way too complex to model.
Exactly. The Hubbard model doesn't capture every single detail, but it does a pretty good job of representing the key interactions.
And what's amazing is that they were able to reproduce some of the key features of cuprate superconductivity using this model.
That's right. It's a huge computational achievement. Simulating these materials has been a major challenge for a long time.
So does this mean we finally understand how high-temperature superconductivity works?
Not quite. But it's a big step forward. It gives us a much better understanding of the underlying physics, and it's a powerful tool for testing theories and exploring different scenarios.
All in the virtual world.
Exactly. It's like having a digital laboratory where we can play with the fundamental laws of superconductivity. We can tweak parameters, change the interactions, and see how it affects the overall behavior.
That's pretty cool. And it could potentially help us design new materials with the properties we're looking for, right?
Absolutely. These simulations could guide us towards new combinations of elements, new structures, new ways to tweak those electron interactions to get the superconductivity we want.
So it's like we're getting closer and closer to cracking the code.
I think we are. We haven't figured it all out yet, but each of these breakthroughs, the insulator, the kagome magnets, the simulations, they're all bringing us closer to understanding this amazing phenomenon.
And the potential payoff is huge, right? I mean, we're talking about completely revolutionizing countless industries. Energy, transportation, medicine.
The list goes on and on. Imagine a world with power grids that transmit electricity with zero loss, making energy cheaper and more accessible to everyone.
Or super fast levitating trains zipping between cities in a fraction of the time it takes now.
And let's not forget about the potential for quantum computers that can operate at practical temperatures, unlocking incredible processing power that we can only dream of today.
Okay, now you're just getting me way too excited.
But it's true. The possibilities are truly mind-blowing. And even beyond those technological applications, think about what it would mean for our understanding of the universe.
How so?
Unlocking the secrets of high-temperature superconductivity could lead to fundamental breakthroughs in physics.
Yeah.
It could reshape our understanding of quantum mechanics and condensed matter physics. It could open up entire new fields of science and technology that we haven't even imagined yet.
Wow. You've definitely convinced me that this is a field worth paying attention to.
It's an exciting time to be following these discoveries, that's for sure.
So we've got progress on multiple fronts, right? New insights into electron behavior, exploration of new materials, and increasingly powerful computer models to help us design new superconductors.
Exactly. It feels like all these different pieces are starting to come together.
But before we get carried away with all this excitement, we have one more source to discuss.
Okay, what is it?
It's about quantum information transfer between different systems.
Quantum information transfer, that sounds a bit different from what we've been talking about.
I know, it seems like a bit of a detour from superconductivity at first glance.
Okay. I'm curious, where does this one fit in?
It does, doesn't it? But remember we were talking about all the potential applications of superconductivity.
Oh, right, like quantum computing.
Exactly. And quantum computing relies on being able to manipulate and transfer quantum information between different systems.
Okay, I see where you're going with this.
And that's exactly what this article is about. It highlights a breakthrough in that very area.
All right, I'm all ears.
This research is from Quebec and Delft University of Technology.
Uh-huh.
And they've created a quantum interface that can transfer quantum information between diamond nitrogen-vacancy centers.
Yeah, or NV centers for short.
NV centers, okay.
And photonic time bin qubits.
So two different systems.
Right. And they each have their own advantages and disadvantages for quantum computing.
That makes sense. But what are these NV centers exactly?
They're like tiny defects in the diamond lattice.
Defects.
Yeah, but they can actually trap single electrons
I see.
and act as quantum bits or qubits.
Okay, so that's how they store quantum information.
You got it. And photonic time bin qubits, they use the arrival time of photons to encode quantum information.
So one uses trapped electrons in diamond and the other uses photons.
Exactly. Two very different approaches.
And this new interface, it connects them somehow.
It's like a bridge between them.
A bridge, a quantum handshake, if you will, allows them to talk to each other and exchange quantum information, even though they're based on totally different principles.
That's pretty amazing. But why is that so important?
Well, think about it. This opens up a whole new level of flexibility in building quantum computers.
Flexibility how?
Imagine being able to combine different types of qubits, each with its own strengths.
Okay, so like a hybrid quantum computer.
You got it. Could be much more powerful and versatile than a system that relies on just one type of qubit.
So this interface is kind of like the missing link.
That's a great way to put it. And it brings us a step closer to realizing the full potential of quantum computing. I mean, the applications are mind-boggling. Medicine, materials science, artificial intelligence.
Yeah, we're talking about solving problems that are simply impossible for even the most powerful classical computers today.
It's a whole new frontier. And that's where superconductivity comes back into play. Remember.
Ah, right, because superconductors could be crucial for building these quantum networks.
Exactly. Imagine using superconductors to create the components for quantum computers and communication devices.
Super efficient, low-noise components that could operate at much higher temperatures.
Right. That would be a game changer.
It would. It could be the key enabling technology for this whole quantum revolution we're talking about.
Wow. We started with superconductivity, went on a little detour into quantum information transfer, and now we're back to superconductivity again.
It's amazing how it all connects, isn't it? It just goes to show that science is full of these unexpected connections.
You never know where a new discovery will lead. But okay, let's bring this all together. We've explored 3 really fascinating research breakthroughs today.
We have the weird insulator, the kagome magnets, and that incredible simulation of high-temperature superconductors.
And we even touched on the world of quantum computing. So, the big question is, what does all of this mean for the future? Are we on the verge of a superconducting revolution?
That's the million-dollar question, isn't it? And if I had a crystal ball, I'd tell you. But honestly, it's just too early to say for sure.
So no flying cars just yet.
Haha, not quite. But the research we've talked about today shows just how far we've come in understanding these complex phenomena.
And with so many brilliant minds working on this problem, I'm optimistic.
Me too. There's a real sense of momentum in the field right now.
It feels like we're on the cusp of something truly groundbreaking.
Yeah.
But before we wrap up, there's one last thought I want to leave our listeners with. What if the key to unlocking room temperature superconductivity?
Yeah.
What if it's not about finding some exotic new material? What if it's about learning to control the behavior of electrons in the materials we already have all around us?
That's a really intriguing idea. It's like we've been so focused on finding the perfect material that we've overlooked the potential of what's already here.
Right. What if the answer has been staring us in the face all along?
It's definitely a possibility worth exploring. And if we can crack that code, the implications would be, well, they would be revolutionary.
No doubt about it. That's some serious food for thought. Well, we've covered a lot of ground today, from the basics of superconductivity to the very edge of quantum technology. It's been quite a journey.
It really has, and it's been a pleasure exploring these ideas with you.
The pleasure was all mine. And to all our listeners out there, thanks for joining us on this deep dive. We hope you've learned something new today and that you'll keep exploring the fascinating world of science and technology. Who knows, maybe one of you listening will be the one to finally unlock the secrets of room temperature superconductivity. Until next time, keep those minds curious and never stop asking questions.